Right, so in this situation here, you've got two particles, A of mass 4, B of mass 3, connected by a light string passing over a smooth pulley. And initially, the particle A is at rest, okay, on the plane, so it's touching the ground there. Particle B hangs at a depth of 1 meter below the pulley, right? So this distance here is 1 meter. What happens to it then? So if we read the question then, particle B is then raised vertically a distance of 0.9 meters, released from rest from that position. So I suppose if it's raised, then of course this distance then from the pulley would be 0.1 meters, wouldn't it? If that's any relevance, I don't know, we'll see now. So it says then, calculate the speed, okay, of B immediately before the string tightens. Okay, so basically it's going to be released, and if you think about it, because it's going to be released from here, from rest, so it's going to fall freely under gravity. Okay, because there's nothing holding it back. Okay, this string is going to be slack. Okay, until it tightens, and they want the speed when it tightens. Okay, so if you think about it, right here now we can sort of approach this situation now and think, okay, well it's released from rest. Okay, so that means initial velocity is 0, okay, falling freely under gravity, so we could say acceleration is going to be 9.8, alright, and we'll take downwards as positive, yeah, because it is moving downwards, okay, so because its direction is moving in, we take that as positive, and of course acceleration goes down, so that's positive 9.8 then. Now we've also got the distance going to travel, 0.9, okay, meters. So we want the speed, don't we, at the end of that 0.9, just before the string becomes taut. So we can use equations of motion, right? So in this case, using v squared equals u squared plus 2as. V squared will equal 0 squared plus 2 times 9.8 times s, which is 0.9. So we've got this. And we get out, what have we got? 17.64. So then to get v, we're going to square root that. Square root the answer, and we get 4.2 meters per second. Okay, so that's the speed it's going to be. Remember now the question was calculate the speed of B immediately before the string tightens. So basically, we think of it literally as it tightens, right? On the verge of tightening, so it's going to look as though it's tight. Determine the speed with which A leaves the plane and impulsive tension in the string immediately after the string tightens. Of course, once the string tightens, diagram here now. Once the string tightens, it's going to start to move the whole system, right? So that's the 3 kilogram mass, that's the 4 kilogram mass, alright? And if you think about it, just before it's taut, as it's going to move, it's going at speed 4.2 meters per second, okay? So we've got to consider with these questions the before and after situation, okay? So the before, as it's just about taut, or just immediately before it's travelling at that speed. After then, the after situation, they're going to move. Okay? The whole system, pulley system, is going to move. Now, this will no longer be falling at 4.2 meters per second, right? Because there's an impulsive tension in the string, right? As it gets taut, right? There's sort of like a jerking sort of reaction, and it's going to slow this down, so it won't be as much. Alright, but it obviously will set this in motion, and what you need to appreciate then, they'll set this in motion at the same speed because they are connected, smooth pulley, yeah, strings inextensible, and the string is taut, so the whole system is going to move at the same speed. Alright, so what we do is, quite simply then, we look at conservation of momentum, okay? Momentum before equals momentum after. The momentum before, in this system here, will just be mass times velocity. Okay, this here, it's going to be 0, isn't it? 4 times 0. Momentum after, 3v, okay, for that one, plus this momentum, 4v. Okay, don't worry about directions. Okay, in fact here, I say don't worry about directions. Obviously, it is important directions, but this is moving in the same direction. That's what I'm saying. Don't worry about it, because you might think this is going up, this is going down. But actually, if you think of the whole pulley system, right? Think of the direction of the pulley. They all go in the same way, aren't they? This 4 is going in the same direction as this 3 kilogram mass. Okay. Obviously, it was only going to go around, isn't it? But it's going. It is going in the same direction, even though they look opposite directions. You don't think of it though like that, right? You don't think, oh, that's got to be, you know, maybe that's negative V, that's positive V. Not at all. They are going in the same direction. It just doesn't look that to you. But think about the string, right? The way the string is going. All right. So they're both positive V. So this is 7V. Work that out. You get 12.6. Okay. And then to get V, then you do 12.6 divide by 7. So my calculator, you get 1.8 meters per second. Okay. Then it says the impulsive tension in the string, right? Find the impulsive tension in the string immediately after the string tightens. Well, of course, to get the impulsive tension, we just focus on one of the objects. I'm going to focus on A. Okay, put the spotlight on A. A is the easiest one. So the impulsive tension essentially is the change of momentum, right? That's what impulse is, isn't it? Change of momentum. So, so we focus on A, we could focus on B, but there's less work to do on A, because the change of momentum of A is, it's just 4 times V, which is 1.8 of course, take away 4 times 0, because it was 0 here. And that's important to remember, right? To measure the impulsive tension in the string, okay, in other words, what's happening with the string, well, it's going to be exactly the same as the change of momentum of the body, because the string is acting on this body and is attached to the body. So what happens to the particle is happening to the string. Okay, so that's our answer there.